Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're on chapter 8, water movements. And more specifically, today we'll be looking at subsection D, applications of 1D and 3D models. 1D models have been applied in water quality applications for several decades. With ongoing land use change and climate change, their value in predicting future states of lakes, the likelihood of ecosystem change, and for improving weather forecasting has led to models with several computational schemes and ongoing workshops and user groups for comparisons and further improvements. Efforts for inclusions of lakes in improved weather forecasting and climate prediction includes these authors. Examples of using 1D models include forecasting water quality and evaluation of changes in thermal structure with implications for oxygen dynamics and for climate change. Ongoing challenges include addressing errors in 1D models associated with the 2- and 3-dimensionality of lakes and uncertainties in the reanalysis data and climate projections used as an input data to model lakes over large spatial areas under climate change. So let's review figure 8-41, cross-sections illustrating the results of hydrodynamic simulations over a diel cycle for an embayment of Lake Janoaca in Brazil. So panel A is wind speed and heat flux. So wind speed is in red in meters per second and heat flux is in black. And the time span we're looking at is sometime around the beginning of DOY 272 and DOY 273 and a little change. And on the left side, we have a cross-section of the lake showing the temperature profile of that cross-section. And we have these dashed line 1, 2, 3, and 4 that represents to panel 1, 2, 3, and 4. And as you can see, we have likely like solar noon right around this time, which would correspond to number 2. And then 3 is around sunset. So this is probably sunrise at 272.25 and then sunset at 272.75. On the right side, we have concentration of carbon dioxide that was injected in the macrophyte bed here, and the dispersion of that plume of carbon dioxide in relationship, of course, with the temperature. So right after sunrise, we can see we have a pretty stratified lake. This is probably the time when they injected the CO2 into the macrophyte bed. And then we have a heating event right here, especially. We can see that the surface of the lake is quite warm. And the surface of the lake water is warm here as well. So we have like the seasonal thermocline, and then we have this, this daily, this just temporary thermocline here, and then we have the injection, and then at number 2, we have then that tongue of CO2 that starts to disperse, and it's starting to disperse with the breakdown of the stratification. So you can see that there's actually like a little bit of upwelling of the warmer water, or the cooler water, I should say, toward the surface. And then right at 3, which is right around sunset, we have a retreat of that CO2 plume, and here we have an increase of the thickness of the warm layer, and we're still dealing with a thermocline, especially very pronounced here. And then we are starting to see the bottom water stratifying into the seasonal thermocline as we did in the configuration of 1 here. And then lastly, during the nights, just before sunset at number 4, we are getting back with a stratification, like a seasonal stratification that we had at number 1 at 4 here. And then here we have, like, due to eddy turbulence at night, we have the off-gassing of CO2 to the surface of the lake. Let's look at now figure 842. So figure 842 is for a different lake. It's Lake Pleasant. And here, we are not dealing actually with injection. We are dealing with simulated CO2 concentrations. So on the first panel, we have the wind speed and in meters per second. And here we have the wind direction so then we have the cross section that is shown here on the dashed line that corresponds to here. So here are the cross section configuration maps, and here are the plan view maps of the lake. South is to the left, north is to the right. These are the panels that show temperature. These are the panels that show partial pressure of carbon dioxide and in ppm. And here we have we have concentration in the brown field, which is greater than 1200 ppm for CO2. So this is a cross section again, that from south to north. And those red lines correspond to the time when the data was collected or ran through the model, I should say. And so we have three events where the model was run to generate those maps. And so what we see here is all of this is simulated, right? So the first thing is the temperature is warmer on the north side here, and we see a little bit of it here in that area here. And the concentration of CO2 is pretty high in the deeper part of the lake. So you can see that. And there is actually some amount of some off-gassing of that CO2 into the upper part of the water column. And then the other thing that we can see is that the concentration of CO2 here decreased. There is no CO2 that is generated very likely by the degradation of biological material at the sediment interface. All right, let's move on. 3D modeling has provided considerable understanding of lake hydrodynamics. These models can represent processes such as the Kelvin and Poincaré waves in basin in which rotation is important and gyre formation due to complex basin morphometry or spatial variability in the wind field. These authors provided an approach to reduce numerical diffusion in the vertical, that is, the apparent mixing due to computational error. Subsequent challenges were to capture the nonlinearity in the internal wave field. These authors provided the first demonstration of the highly nonlinear internal waves predicted in Horn, and quantified the considerable increase in eddy diffusivity from these internal waves. These authors captured the nonlinearity of the internal wave field in Mono Lake. Further, they showed upwelling regions rotating around the lake due to Kelvin waves when wind direction remained stationary, but also due to changes in wind direction. This latter observation was anticipated and implies that upwelling regions can rotate around basins too small to be influenced by Earth's rotation. By changing the morphometry of the lake from its horseshoe shape to progressively less complex shapes, modeling results illustrated that complex basin shape reduced the potential for mixing an additional result allowing extensions and predictions to other lakes. Other examples include modeling of Lake Janoaca and Pleasant Lake, with implication for predicting evasion of climate-force trace gases, establishing the links between storms, inflows, partial weather patterns, and primary production in Arctic lakes, illustrating the movement of sediment-laden river water with high nutrient concentration from an embayment to the main basin in Lake Victoria, with implication for the development of harmful algal blooms and the links between the spatial distribution of large and small-bodied zooplankton to internal wave dynamics. 3D modeling also contributes to improve accuracy in computing lake metabolism. Earlier and ongoing 1D and 3D modeling efforts combined with observational data have provided considerable understanding of hydrodynamic processes and the functioning of aquatic ecosystems. Summary: water movements in lakes and rivers occurs in response to wind, cooling, and gravity. Below a certain speed of flow, water movement is smooth and undisturbed along interfaces. This ordered movement is called laminar flow. As the water moves along an interface such as the bottom of a stream or water of a different density, shear stresses result due to friction. As the velocity increases, vortices occur as a result of the shear, that is, the change in velocity away from the boundary of the interface. The flow is considered transitional. With further increases in velocity or with disturbances at an interface such as rocks or stream bed, the flow becomes chaotic and dispersive, that is turbulent. In a turbulent flow, the largest eddies generated by the stirring agent break down into progressively smaller ones until at the scale of the smallest eddies, gradients in heat or solutes are removed by diffusion and the fluid is mixed. The velocity of a turbulent flow is the sum of the mean velocity u and the velocity fluctuation u prime. Here, u and u prime imply velocities in all three directions. However, when the velocities are fully specified, u and v are horizontal velocities perpendicular to each other, and w is vertical velocity. As the velocity fluctuation averages to zero, the root mean square velocity, RMS, is computed, that is u prime square with bar, with this term called the turbulent velocity scale. It is approximately equal to the water friction velocity of u star w. So we already went through that equation, so I won't do that again. The amount of spreading induced by turbulence is quantified by dispersion coefficients, and the amount of spreading and mixing is quantified by the coefficient of eddy diffusivity. Both are identified by the symbol K and are proportional to the product of the turbulent velocity U and length scale L, that is K is equal to CUL, where C is an empirically determined coefficient. Epsilon, so let's see here, turbulence on the largest and smallest scale are related due to the flow of turbulent kinetic energy from the largest to the smallest scale, such as epsilon is equal to u cubed divided by L. The magnitude of horizontal dispersion, KH, is usually orders of magnitude higher than that in the vertical, with empirical work showing that how KH varies with the length scale of the diffusing patch. Fluxes of momentum in the vertical are the product of turbulent velocity fluctuation in the horizontal and vertical. That is less than, so x is less than u prime, w prime, and greater than x or z. And fluxes of heat or other scalars are similar than t prime, w prime, where t prime are the fluctuation of temperature or another scalar. These fluxes can be calculated as the product of the coefficient of eddy diffusivity, Kz. Water in streams and rivers flow directionally along decreasing elevational gradients. Turbulence results from the shear from the friction of the water against the sides and bottom of the channel. The hyporheic zone is the wetted region below a stream bed into which groundwater flows. As the morphometry of the stream channel changes, stream water downwells into the aporheic zone and subsequently upwells. Movement of air over the water induces currents, and depending on wind speed, oscillating motion called capillary waves or surface gravity waves. While water entrained in surface waves oscillates considerably, up and down horizontal movement is small. Currents are non-periodic water movements. Although many external forces contribute to the generation of currents, wind is the dominant driver of surface currents in open water. The velocity of wind-driven currents near the water surface is about 3% of wind speed. Langmuir circulations are helical motions that result from the interaction of wind and surface waves. They form at wind velocities greater than 3 meters per second. They move water and entrained particles in a spiral manner, approximately parallel to the wind direction and that of surface waves. Surface seiches results when wind-driven currents cause water to accumulate downwind. They affect the motion of the entire water mass of the lake, whether stratified or not, and have maximum amplitude at the surface. Wind causes surface currents that move water downwind. A return current occurs above the metalimnion. The increased volume of water downwind causes the thermocline to downwell downwind. The degree of deflection depends on the Vandenberg and lake numbers, and it determines the shear across the thermocline and any mixing between the different layers of the lakes. The thermocline tilts downwind in response to the increased pressure when wind-induced currents transport surface water downwind. Internal waves can be described based on their mode and the number of nodes. That is, the first vertical mode, first horizontal mode V1 H1 internal wave has uniform thickness as its upper and lower extent across the lake basin and oscillates about a node at the center of the lake. A second vertical node, first horizontal node V2 H1. The extent of wind-induced tilting of the thermocline varies with the stratification across the metalimnion, the thickness of the upper mixed layer, wind shear, and the length of the lake in the direction of the wind. These variables are incorporated in the Vandenberg number and related lake numbers. Internal waves of various types occur in stratified lakes. Internal waves can be induced by wind, as described above, and also results from disturbances such as those from a river inflow flowing as a gravity current within or at the bottom of a lake. Exchanges between inshore and offshore regions are caused by density differences in the horizontal. These flows are a form of horizontal convection. In winter under the ice, low currents occur in lakes, or even despite ice cover, reducing the influence of wind and the lack of appreciable inflows and outflows. In spring, a narrow zone of warm water can develop between the nearshore and offshore. The shallow nearshore waters can continue to heat more rapidly than the open water, such that the temperature exceeds 4 degrees C, whereas that offshore is below 4 degrees C. River water flowing into a lake or reservoir initially mixes somewhat with lake water, and dependent on the resultant density, either flows into the lake at the surface as an overflow, intrudes at depth where its density is similar to that of the lake water, or if its density exceeds that of lake water, flows towards and along the bottom. The motions within lakes consist of many interacting processes acting over a range of temporal and spatial scales. By use of timescales such as those for advection, mean velocity divided by the length of a lake, mixing L squared divided by Kz, where L is the length scale for the region of interest, and reaction rates such as chemical conversion or growth rates, outcome of the interaction of hydrodynamic processes and chemical or biological ones can be predicted. Hydrodynamic models have been developed whose complexity varies from describing an individual process to the many interacting processes as they change over time. And that will be it for today, and thanks for your attention. I'll talk to you tomorrow. Thank you.